Welcome back to the second part. Just now the video was cut off because the video only allowed me to record in a 5-minute section. So I stopped at saying that the difference between the intercept over here and the true value represents the error. And if we observe enough data, okay, if we do enough of these prediction by trying to fit as many lines as possible, then we notice that the error is normally distributed, and this is also notated by this normally distributed looking line over here in uh, each of these x vertical line. All right, and we also notice that each of the x value is not affecting each other, isn't it? Therefore, we can also conclude that the error is normally and independently distributed. Okay, hence we conclude as such, right? The error E is normally and independently distributed. But remember this, yeah, must always remember this, that the true regression line is not known in real life. Instead, only the fitted line can be found. So we are trying to find the best fit as best as possible. Okay, so by taking one of the x in this example and putting it into 2D, this is what we are seeing. So this is the line that we have just now, the mu. Okay, the example that we used just now, the mu, the same line. And this is a true response value, and this is the error, right? This is the error E. Okay, because this is one of the fitted line, right? This is also one of the fitted line. So this fitted line give a response here, but instead the true value is here. And let's say let's generalize this even further, right? Instead of mu now, I say y. Okay, y with the hat over here, y hat. We generalize our discussion even further. Y hat is alpha plus beta x. Okay, as you know. Okay, it's like another regression line. So another regression line of y hat here will give me another error. Let's call this error E over here like this. Based on this regression line, the x value will give a response of here, but instead the true value is here. Okay, so the objective now, if you can predict, right? When we try to find the best regression line, our objective is trying to minimize the error as much as possible, isn't it? Therefore, the entire objective of deriving the regression line is to minimize the error E as much as possible. As such, following that, if we minimize, okay, a true value of yi, this is a true value of yi, minus the y hat, which is the response given to us by our predicted, our fitted regression line. The difference between the true response, and also the predicted line will give us an error E. So if we can minimize E over here, then we have found our best fitted regression line. And therefore, we do this, the sum of square error. Why we want to square? Because it's just to remove the negative values. Sometimes we predicted that the value is higher, so y minus y hat will become a negative value. Sometimes we predict that the y hat value is lower, y minus y hat is positive. So the positive plus negative, it will cancel off each other. So in order to avoid that, we want to take the absolute value only, we square the error. That's why we call the sum of square error. So the sum of square error, the SSE, if we do that, okay, and we expand this equation, it looks like this, right? So this one we know. Yi minus y hat, this is y hat, okay? A plus bx, okay? Alpha plus beta x is the same thing, right? So we want to minimize this. So to minimize this, we have two parameters over here. We have A and we have B. So we take the differentiation of this SSE over A equals 0, and the differentiation of SSE over B equals to 0. Because when you do the differentiation and you equate to 0, then you either find the maximum or the minimum, isn't it? So this is the minimization problem. So we get the minimum value of A, the minimum. So we get the A and B that give us the minimum error. Okay. So to simplify the derivations of the mathematical equation, we conclude that B finally have this rather long equation that you can use to calculate B value. And if you have found B, then you can use this equation